Okay, that's good. Thank you. Anyway, that was a nice break. So the idea is that we should be accessing preserving locality. If the lines are row major laid out and the cache line worth is fetched, we should keep the locality in mind. This access order gets a cache line, but it doesn't use the cache line, gets the next cache line, and you soon the capacity conflicts come and throw away the old cache line. When you're back here, that cache line is not there, so caching is important to keep in mind. The same pattern is relevant for matrix multiply. If you write it in this textbook way, which is usually used to teach sequential programming, so this is how you multiply 8 AIK BKJ gives you CIJ. That's good for sequential programming, but it's terrible for even sequential programming. It's not good. This is a sequential program, okay? So this is sequential. It's bad for sequential program. Yeah, and the idea is that you see which index is traveling fast. So BKJ. So this is an example by many people, but these slides are from Dr. Paul Kelly. I have his name. So BKJ means you fetch this much cache line worth, but you use this much, and then you get the next cache line. So it's a lot of cache evictions. It's a bad style, and the performance is telling. You can read these slides since it will be available later. So apparently, okay, so for n equal to 1020, okay, let us see. Okay. So I'll show you the full thing. So yeah, for n equal to 1020, the initial version ran in 130 seconds for Paul Kelly. It's a O n cube algorithm, so that many steps, that's the work. So now you know what work means. That's the number of steps in AIK, BKJ, each number of computational steps. And apparently matrix multiply has high degree of parallelism. I forget the work and depth, but you can look it up. I'll tell you later. But since we looked at work and depth for sorting and all that, for matrix multiply, work T1 by T infinity is very high. Anyway, that aside, it's not yielding, it's not parallelism yet. We are not parallelizing it here. That's only a side point. But the number of floating point operations is very low. So he even says that finally it is 19.8 megaflops. That is, if you look at the processor clock, it is like one floating point operation completed every 80 clock cycles, which is bad actually. A single floating point operation doesn't take 80 clock cycles. So this is adding a lot of extra overhead. It's not the flop of the processor, it's showing up the cache miss penalty. So how are you going to get the value for the money? This is Paul Kelly. He's one of the experts in this area. Interchange loops, that's it. Make it KJ. So it's same IK, BKJ, but now J is traveling faster than K. So in this case, you can draw pictures and figure out. This is CIJ. CIJ is nicely going this way because J is traveling faster than I, so you are still sweeping this way. This is AIK, it's a singular axis there. BKJ, no, this is what we are looking at, sorry, not this one. So BKJ, but J is traveling faster than K, so this is also row major. So this is much faster, okay? And good, so faster. And there are some graphs that you can study to convince you. But independent exercise to this class, this is, you can implement these in your machine and speed benchmark. That I have provided code for that. But question to the class, will you get bitwise identical answers? I just briefly talked about reassociation. Remember our dot product and other things where this was worse than the balanced. So the question is reassociation happening here? I'll tell you the answer tomorrow. Why don't you think about it? Are the matrix multiplies written these two different ways? You can draw some pictures and even write out simple examples by hand. See whether you are getting a different tree of addition finally, okay? You're multiplying and adding, adding. Is the tree shape different? We'll tell you the answers tomorrow. We can even take a majority vote and see who agrees. Maybe that's good. Okay, it's a simple exercise. The answers are fun, like in this. So these are the questions one can ask. Fault sharing, that's the next topic. So locality is important. Fault sharing is hugely important. I'm going to ask questions not to make a point or anything, because we are all trying to learn together, but how many of you have heard of fault sharing, just to know? Yeah. Good. Okay, so some people have heard and some people are sort of aware of what I'm talking about. We'll tell you more. Okay, good. Fault sharing is one where you didn't mean to really, you are not really sharing a single location, but something else is being shared. It's the cache line you are sharing. You're sharing a cache line, but different processors are biting on different piece of the cache line. This is a good cartoon for fault sharing. Okay, it's a long bone, like a cache line is long, and different dogs are chewing different parts. Fine, but they need to get exclusive access to the cache line before they can chew, even though the parts are not overlapping. So the bone flies between dog and dog. So you get an exclusive access to the line, but I only want to chew here. The other dog wants to chew here. And that back and forth flying of lines is bad. It's really going to tank performance. You can measure it. You can see it. So this is a code you will write. I mean, look at the size of code you have to write to illustrate these. I mean, it's not rocket science. I just happened to think of these quickly one day, but you can run this code, and now you are running under parallelism. Okay, this is an experiment to run on parallelism, because you're talking about cache lines, and cache lines being shared across two threads or two processors, and you want exclusive access. So no, this is not a sequential example. This is a parallel. So this is the parallel thread function that you'll be spawning from p threads. The surrounding code is not shown here, but once this code is spawned, each thread is simply doing what? Each thread is only doing getting its own rank. I may be thread 0 or a thread 1. Then I am taking my thread rank and multiplying with a padding factor. Padding factor is only large enough, it can even be 1. So even if padding factor is 1, my rank could be 0. So this guy is doing 0, a of 0 plus plus. The next thread is doing a of 1 of plus plus. They are not falling on the same word, so everything is fine. But they will fall on the same cache line. But now keep increasing the padding, and at some point the performance will really increase, and you can run that and discover at one point. So some of your exercises are as simple as writing a loop around this and plot a graph of when the performance suddenly increases, and that will immediately tell you, yeah, cache fault sharing is for real. So you have to move the thread sufficiently away to avoid fault sharing. This is faced in OpenMP programs. So OpenMP programs have this problem. You have to be fault sharing aware. There are ways to avoid that by writing different code, but the first code you write tends to have fault sharing. GPU code, on the other hand, likes this access pattern. GPUs have been designed in such a way that each thread accessing adjacent locations is preferred. So A's of 0 getting accessed by thread 0, A's of 1s getting accessed by thread 1. That is good for GPU, bad for OpenMP. Because GPU's memory system has been designed that way, such that you have to, the memory is interleaved in such a way that adjacent threads accessing different adjacent locations is supported. This is a problem also. So people sometimes write GPU code, OpenMP code, and try to migrate it to GPU. They'll have to do some work because the performance doesn't port. What is good for GPU is not good for OpenMP. And I told you this system called COCOS automates this conversion with efficiency. So this is why we really need tools to do this work for us. It's a lot of work to do it manually without errors. So these are not simple tools. Please don't believe that you can. I don't believe it, at least, that you can download Cocos and use it. It's still too complex, as I understand. But why not? Give it a try. If it doesn't work, write to the Cocos users. They are a very friendly group at Sandia. So many of these tools could be sophisticated, but on the other hand, sometimes these researchers engage with the groups and help them along. That has happened. Anyway, so keep these in mind is all I'm saying. But it may not be immediately successful, but it's going the right way. 15 minutes for a hugely important topic, but I will talk about it efficiently. The third thing is avoid data races at any cost. And it's a problem I cannot stress enough. Any shared memory programming in OpenMP or thread building blocks or GPUs is an act of preserving data dependencies in the code while avoiding data races. It's almost like a tightrope walk. We had to walk along the rope and not fall off. Again, the code you see is not the code you run. That's an important thing. So let's start with the data race. So to have a data race, you need a few simple things. One is you should have at least 2 threads, otherwise there's no data race. One of the threads must be doing a write. The other thread may be doing a read or a write. And there is no synchronization. That's when a data race happens. Why? Well, intuitively the idea is like racing. I am racing to grab this token, but another person is also racing to grab that token. Who gets it? It's not clear. That's the first thought. And that's the usual thing. Like if I withdraw $20 from a bank and write back 20, somebody else is doing the same thing, or I'm withdrawing 10 rupees and somebody else is adding 100. If that happens concurrently, sometimes the effects are in the database is in the stale state, and one of the writes will succeed the other. The amount may be not the correctly balancing addition. Checkbooks may not balance, but that's not the only thing. What the code you see is not the code you run is the real culprit. Let's get there slowly. So normally when you want to eliminate data races, you put a lock and unlock instruction. It's as if you have a lock and a key on the database. So you lock and then you unlock, and then only this lock can succeed, or this can, this can lock and come to unlock, and then it can enable the lock. So one of these orders is expected. Well, that's shown this way. So these are called happens. So this idea of happens before is widely used. I will slowly introduce it. But logically, there are 2 executions that are allowed. One is that one, and the other is that one. So depending on how fast the threads run and how you interleave, one of these outcomes is expected. This is obvious from locking and unlocking, but this is not the only way to ensure happens before. This is why I am saying happens before is the logical order. What other things are possible? When things are not ordered, they can be interleaved in time in different ways, and they are not required orderings. So for instance, so if I pick 2 instructions here, X and Y here, when you display the time order of occurrence of x and y in one interleaving you may see x happen before y in time order, or in time you may see y before x. This is just an accident of how the threads ran, and these are not in both these are okay, they are not in the happens before. So there is no happens before between x and y, because x is happening after the unlock. So how soon do you get to unlock? It depends on your speed, and when you unlock you are enabling this thread, and how fast does this thread reach to y, that depends on its speed. So there is really no required ordering between x and I'm sorry? Oh, battery, I see. I'll connect, thank you. So there is no required ordering between x and y. So that's not happens before ordered. So happens before order is the necessary order. So this graph is really showing the necessary orders that needs to be obeyed in any execution. That's why happens before is such an important idea. We think of all other orders as accidental orderings that happens to be there in time order. That's what happens before means. This is one way to, thank you, got it. This is one way to ensure happens before. Another way to eliminate this is not using locks. Locks are very slow. Many locks are very slow. Some locks are okay, fast. But if you can avoid locks, use other types of synchronization. So if your communication pattern is you are producing something here and you are consuming it here, don't use locks and arrange it. Use release acquire synchronization. And what that means is that you are basically providing a fence operation here that reliably posts the values you wrote before, so that when you observe the value of this variable here, you can be sure that it is this value you are seeing. It's kind of like putting a while loop, while one wait busy loop here. So this could be a busy wait, and this could be a flag equal to 1. But you have to use special instructions so like Java volatile or C11 atomic. You're going to learn about this in a very fun way. Why these variables matter is not obvious unless you write one program that surprises you, and you're going to write that. You can't use ordinary variables, you have to use special variables, and special variables are variables which the compiler knows about and puts a fence. So that's why release and acquire are important. I'll tell you in a second. A third way to eliminate data races is to use a barrier, like what we do in GPU programming. This also gives you a happens before order. So there are 3 basic ways to avoid data races. You need to avoid them. Otherwise, you are having a racing access. And I haven't told you the real bad news yet. Why eliminate races? Not the non-determinism. Popular answer is non-determinism, but it's a very loose idea. But the real reason is the execution order is still non-deterministic. So that's not what we are talking about. You could have run this order, or you could have run this order. That's non-determinism according to some people. But that's not the non-determinism that should worry. That kind of concurrency non-determinism is part of concurrency. You cannot possibly have a lock content and clear the same way every time. That is expected. There is something deeper going on. It's the pink elephant. It's my best drawing of a quick drawing of a pink elephant. This term was coined by Herb Sutter. We know that pink elephants don't exist. But pink elephants suddenly show up in program debugging. Hence he said, yeah, look for pink elephants. They are unexpected values. You never wrote 23 in your program, ever. But somehow in a location, you didn't do any arithmetic, let's say. You're just writing and reading. That's all. Suddenly managed to read 23. You never wrote 23. That's bad, right? No addition, no nothing. Okay, so how can a read-write program produce 23? That can happen if you do data races. So this is what compiler optimizations do to produce pink elephants, i.e. reading values you never wrote. These are real, okay? These data races are real. They have stricken important code. And we are going to study data race detection tools. So very important to know these tools. Most people, I would say 50% of the people, let me say safely, out there in concurrent programming language land don't know what data races are, don't know how to detect data races. At the end of this course, at least you will be one crowd who knows exactly how to go after data races for pthreads and OpenMP. I can give you certain insights into my specialty like that, floating points thing. Okay, this is a funny program, right? You externally saw x equal to 0, and you read t equal to x, and you expected t equal to 0 here. And when you ran the code without compiler optimization, that was fine. You turned on optimization, you found that your original program was changed to writing x equal to 24, and it is picking up 24, but you never meant to write 24. How can that happen? So this is how it can happen. You didn't tell the compiler that you are intending to synchronize across two threads. There's only one way you can tell a compiler that you intend to synchronize across two threads, either by mutex around the synchronization points, or you use a special variable called Java volatile or C++ atomics. In C, that variable type is still not available other than in C11. Anyway, so if you tell the compiler will be safe. If you don't tell the compiler that this is an intended point where I am writing x equal to 0, I'm going to read in a while loop x and hope to get out, but you didn't use a special variable, the compiler can do the following thing. In a hypothetical example, it might see x equal to 0. Okay? Compilers do their work only across a single thread. All compilers are optimizers of code along a thread's execution path. Compilers never try to, most compilers never optimize code across threads. Okay? So a compiler's job is, given a thread and a thread of execution, it can do the best to collapse that thread of execution. It sees x equal to 0, it sees y equal to 23, it sees x equal to y plus 1. A compiler can do the following thing. It can observe that y equal to 23, analyzing somewhere in the code, calculate this during compilation to be 24, put this to be 24, then it sees there is no use of x here, so why not 24, save some instructions. So it can replace this entire code with that one, and y equal to 23. That's a legal transformation for a sequential compiler. In fact, sequential compilers are doing these things all the time. We don't know, but we never look at assembly code, right? If you look at assembly code, you'll see strange things. It can tear a word into half, do an XOR, do various rearrangements. Nobody sees it. If nobody's looking, you can do anything dirty, right? That's the thing. So compilers do it. But as soon as you look, you have to tell the compiler, this is an observation point. Then you don't have the dirty laundry show up. So if you do mark these variables as special variables, this never is allowed. And that's why pink elephants are manufactured. So a lot of optimizations are prevented if you tell the compiler that this is a special variable. I'll tell you more about it. You will get one example to use as a start. So there is no such thing as a benign data race. Many old books and many old-fashioned writing of C code gives you racing programs. I have one example from a celebrated book, but one or two examples are the old-fashioned C code, which has a data race. I've seen in a certain framework one piece of data race. These things are waiting to die badly under some situations. This actually happened. So we were called to rescue, collaborate in a project where at the Lawrence Livermore lab, they were porting an application called Hydra, and this is a large multiphysics application. And they found that whenever they turned on multi-threading and optimized the code used to crash. They went on for some time, and finally they said, okay, we are not going to parallelize that loop. OpenMP parallelization is by putting a pragma around a loop. And they took away the pragma, made the code sequential. The problem went away, but performance went away too. So finally, we applied our data race checker and discovered that two threads were writing 0 to the same location without synchronization. That's it. So somehow one variable was written by this thread with this thread, no mutex around it, no special variable used like a volatile variable or a C++. The compiler was not writing 0. It was happily tearing the 0 into pieces, mixing it with code surrounding it, it had no idea that 0 was intended to be written and synchronous. Right. So that was the code crash. We can't tell why, because the real results are hard to know once you see a crash. So how do you detect? This is an actual textbook code. Professor Pacheco's books are great, but he still has an old-fashioned use of a racing construct. Don't write this code. While my flag not equal to my rank, busy wait, and another thread is going to set flag and rescue this busy wait. So set and test is normally fine, but in this case, if this code is optimized, it is asking for trouble. You may never get out of the while loop. But the way to correctly program that is to use a modern dialect of C or C++ and say atomic X atomic type for C++. The name changes from language to language. GPU also has pink elephants. I can show you a pink elephant we discovered in GPU. Under no optimization, this was the answer, and under optimization, this was the answer. And this code has a data race in it. We'll discuss that later during the discussion time, or when GPUs are discussed. I'm saying that OpenMP and GPUs have this read-write conflict where read and write can overlap. This is a write, this is a read or write. That's without synchronization, it's bad. What exercise? Okay, what's this? I'll take one more minute. I think I'm almost time. What's the story of data race detection? We need a checker, right? So these data races are so hard to eyeball and figure out. You can't read a code, you can't run it, test or you need a good tool that tests for data races in a very thorough way. It's still not foolproof, but it's much better than manual. P-threads, we have support for data race detection thanks to modern advances from Google research, which has gone into GCC and Clang. So you will be running some GCC experiments with a -f sanitize flag, sanitize equal to thread flag. That pinpoints data races pretty reliably. You can see some experiments. OpenMP, yeah, we developed one of the first usable ones. There were others that were not at all production quality, but we have, and you have it installed here. Thanks to Dr. Jairaj and his students, we have OpenMP Archer tool installed, so you can try to run that. Hopefully it will install. CUDA, it's available, but there are a lot of them. We don't know which is that good. Unfortunately, for threading building blocks, which is such a great library, it still doesn't have a reliable data race detector. You can use the pthreads data race detector, but it throws a lot of data races. Many of them are not meaningful. Some of them are false alarms. So that's a problem. So I will just show you one experiment you will do, and then that will be it. You will be writing a simple piece of Java program. How many of you know Java? You don't need to know Java to run this. Yeah, Java is kind of around. You just don't need to know, you just need to use this. We are going to write a simple loop like this. This is ready-made. And what this does is extremely simple. One Java thread is going to do n times, request equal to 1, okay, one variable, while not ACK, wait, request equal to 0, while ACK, wait. The other thread is going to do the complementary thing, while not request, wait, etc. So what it's trying to do is a handshake, okay. So let's read this carefully. One thread is going to set a request, which is here. So one thread is setting a request, and this thread is spinning on request going high. So when it gets request equal to 1, it sets ACK equal to 1, which thread is waiting, then it sets request negate, acknowledge negate. You've seen 4-phase handshaking in communication maybe? Yeah. Request, wait for acknowledge. When acknowledge comes, request goes down. When request goes down, acknowledge goes down. It keeps doing that. That's what the loop is doing. Oh, yeah. So that's all this loop is doing. So this is how you write a Java program to do that. We can read this code later. You can see this. Request equal to true, while ACK equal to false, wait. Request equal to false, while ACK equal to true, wait. And do this a certain number of times. But now the experiment is run it in two different ways. One way is to declare it as static volatile Boolean. And the second way is to eliminate volatile. That's it. Just remove the word volatile. That's a magic word. That's how you tell the compiler that you are synchronizing there. If you put volatile in Java, you're telling the compiler that's where you're synchronizing. If you remove that volatile, compiler has no idea. So when you run this code, you will observe that if you don't use volatile, at a certain number of iterations, the code will deadlock and hang. You'll have to control C and come out. It's such a nice illustration of data races being real. So you can actually see the hang after some iterations. As soon as you add volatile, it works. The thing is, the compiler loses the sense of request acknowledge, orchestrating it as optimize the code. It's not the compiler alone that's optimizing. Hardware has something called store buffer. All these are important. HPC is not high performance or high level programming or anything. HPC people unfortunately need to know a lot about how processors work. So processors have something called a store buffer, where I'm almost done. You can write a value and it can be pending in a store buffer, but when you read, you may bypass the store buffer and read if provided the address is different. And the store buffer effect is what we are seeing in this example. It's not compiler optimization. This is because in this program, thank you. In this program, if you reduce the iteration to 200 or so, it will always come out without volatile. But if you keep increasing this number, at some point the rate at which you are putting things in the store buffer and taking out is upset and it hangs. It's a very nice test. If it were actually a compiler who is massaging the code and breaking, it will happen at all iterations. It is not. So this is again such a simple test I happened to discover by chance, and I've been using it such that you can teach data races as real. So I think there were avoid FP I will say avoid, the gist of what I talked about today is avoid floating point round off surprises, avoid non-local accesses and fault sharing, and data races. So we covered these topics. Thank you. So we talked about non-local, round off, fault sharing, data races. Okay. Now we are ready to do our work. I think we have scared ourselves enough. Prior programming is not easy, but it's good to know the dangers. But now that we know the dangers, at least we can at least walk OpenMP and pthread somewhat. So, but tomorrow we'll see some pthread dangers at a high level and OpenMP. So that's what we are going. Okay. So today was basic. Thank you. Yeah, thank you. You can do it. Okay. Don't be shy. Just kidding. Just kidding. Thank you. Anyway.